Okay, hello everybody. Um, I'm Björn. I'm a software developer working at Amazon Web Services, and specifically, I'm on the EC2 kernel and operating system team, which takes care of all the hypervisors and kernels running in the Amazon EC2 fleet. And specifically, I'm in the subteam that deals with hypervisor security, and that includes evaluating all kinds of security issues that we face at the software and hardware level, and specifically also includes looking at Zen security advisories. Today, I'd like to talk about QEMU and Live Upgrade and how we built that and use that in the security context. And I'd start with a story that's a couple of years old now. There was XSA 133 back in 2015. And XSA 133 was special in the sense that it had a code name called VENOM. And it was one of the few XSAs with a real logo. And there was a lot of fuss going on back then whether having a logo for your security vulnerability is actually a good thing or not. And this was one of the first where this discussion really got out of bounds. The interesting thing here is that VENOM was a QEMU vulnerability where the floppy disk emulation that QEMU provides in virtualized environments could be used to overwrite a static buffer somewhere in QEMU. And depending on what kind of data structures were allocated behind that buffer, that could lead to all kinds of bad things happening up to remote code execution using QEMU. So from a virtualization perspective, that was a pretty big thing. People were very worried about that. And a lot of effort was spent figuring out how we can actually fix that. So obviously there was an official patch for that, but people were also considering activities such as hot patching this issue, which turned out not to be completely straightforward, but I'm giving you a link to a blog post here that describes how you could actually, using a ptrace-based approach and knowledge about your running QEMU, as well as how VENOM can be fixed, perform hot patching on a running system. So that was interesting. For us in AWS, security issues at the Zen level are certainly a thing we look at and we consider serious because that is the basis of our infrastructure. So we're also following this very closely. And one of the things we learned there was we need to do something about QEMU, which we obviously had been doing before as well, because there were other QEMU exercises before. But we felt we need to step up the game here and not just say, okay, we're going to apply patches and reboot the end. And what we did then, that's what I'm going to talk about today. So just a quick recap for everyone, although I believe most people would already know that. This is where QEMU sits in the Zen virtualization stack. So we have a Zen hypervisor running DOM0, which is a control domain, and we have guest domains, HVM or PV domains. For HVM domains, every HVM guest domain is assigned a QEMU process running in DOM0 at startup. And this QEMU process acts as a device emulator for this guest. So the guest can issue device accesses, and these will get reflected to the QEMU process, and QEMU then deals with them, modeling the devices. On the other end of QEMU, there are other DOM0 services which also interact with it and that implement additional features that your infrastructure wants to provide. One example for that is in AWS, in the EC2 CLI. In the AWS CLI, you have a command AWS EC2 get console screenshot, which allows you to get a PNG image of your VGA frame buffer. And the VGA frame buffer is the device that is emulated by QEMU. And we have a service that uses QEMU's VNC implementation to actually talk to QEMU to obtain that and then deliver it to you as the customer through this command. So QEMU is a bit different from your standard Zen hypervisor security vulnerabilities. And it's different because operating QEMU works a bit different from a hypervisor. We have a single hypervisor running on a single host, and in order to update it, you either hot patch it using something like live patch, or you reboot your server into a new build of the hypervisor. For QEMU, there are a couple of differences. One is there's one QEMU per running instances. So if you're multiplexing your hardware among different instances, then there will be multiple QEMU processes. The interesting thing here is that the QEMU process will be running as long as your instance is running, which means if you have a very long running instance, then your QEMU process will also be running very long. And any fixes that you ship and that you install in the meantime will not affect the running processes. And the experience from EC2 tells us that there are actually instances that are running very, very long. But there is a certain amount of instances that are periodically rebooting because people use autoscaling, because people run Windows instances and every month do reboots because of Patch Tuesday. We also see customers running the same EC2 virtual machine for months or for years. And for those, we have the problem that from a security perspective, we cannot just apply a patch because just shipping a new QEMU to this host will not fix anything for the running processes. This is in the best case an annoyance because you just feel like, okay, you haven't fixed the whole fleet. In the worst case, this is actually dangerous because depending on what kind of vulnerability you have, if you have something like a remote code execution in QEMU that gives you essentially remote code execution inside DOM0, then even if you have a single instance that is not fixed against the issue yet, you're basically posing a risk on all the other instances, even if they're running a fixed QEMU. So this is an operational problem. Another thing is that due to operational comfortability, we're using EC2 in a way where we allow to ship newer builds of the Zen runtime components, including all the user space components, and run them on older hypervisor builds, which means over time we can accumulate multiple different versions of QEMU running on a host. And that means when we want to do something like fix a security issue, we have the additional issue that now we have multiple QEMU processes running, and they can actually be running a different build of QEMU, and depending on this build, we might be willing to do different things. Having some experience with hot patching at the hypervisor level, one of the first things we considered or analyzed was, can we apply hot patching to QEMU as well? And it turns out it's not that easy because there are a couple of reasons that make QEMU XSAs or that made QEMU XSAs at the time more complicated. And more complicated means the patches were bigger, there were larger diffs, there were more functions touched. And while it's possible to hot patch this kind of stuff, it is more dangerous because you have to cover more different cases. You have to make sure that all this still works after hot patching, and you have to have just more testing and spend more time verifying that things work properly. And on top of that, there are a couple of things like QEMU XSAs more often came with data structure changes, and this is something that is difficult to operate from the hot patching perspective. So instead, what we tried to do there is we tried to implement life upgrade for QEMU, and this is what I'm going to talk about now. So in order to get life upgrade to QEMU in Zen, we need to solve three different problems. The first problem comes from the fact that we might have multiple different versions of QEMU running, and we need a runtime mechanism to actually figure out which version a certain process is running. The second thing is, once we know what kind of QEMU build we're interacting with, we need to have a way of getting this QEMU build to re-execute a new version of QEMU. And the third thing is, given that QEMU is stateful, we need to have a way of transferring state from the old QEMU to the new QEMU. And let's start with the first problem. So for version detection, there is a fairly straightforward solution, and that comes from a linker feature. So if you're using GNU LD to build or to link your QEMU, there is an option to LD called --" build ID. And what that will do is when linking QEMU, the binary, it will add a new elf section, and that elf section will contain something like a 256-bit hash sum of your build. And that 256-bit hash sum is unique enough to compare versions and actually identify the currently running version of your build. So that was the first thing we did. We added a feature. So we added using --" build ID to the QEMU linking process, and we added a mechanism so that QEMU upon startup publishes its build ID inside XenStore, so that any DOM0 component that wants to figure out the version can actually do so and figure out which version is running. Now we come to the operational problem number one. We might have older builds at the time. So in EC2, we operating servers for a long time, and we added this build ID feature somewhere in the middle. And that means we already had lots of processes running in the fleet that didn't have the build ID feature. So in order to determine the version that is running there, we had to do a kind of a trick. And the trick was that we built our own poor man's version of the build ID detection by looking at our old builds in a database. And it's a strong argument that I'm going to make here, and it's if you take one thing besides the QEMU life upgrade feature away here, is if you're operating cloud infrastructure, you want to have a database of all your historic builds so that you can go back in time at some point and analyze what's actually potentially running in your fleet. Based on such a database, what you can do is you can take all your builds, have a look at certain things that get loaded into memory, such as the text segment containing the code of the QEMU binary, and create checksum of those segments. And then at runtime, you can go to the running process, look at their pros pmem, or use ptrace to just dump the same areas as well. And then you can calculate the runtime hash sum and you compare it to your database of potential hash sums that you might encounter. And that way, even without a build ID feature, you can at runtime determine which process to run. So given that, we now have a way to determine all the running versions of QEMU in the fleet. And we come to our next problem. The next problem is, how can we re-execute QEMU? And we considered a couple of alternatives here, ranging from something like, okay, maybe we can do something like a local live migration, where we not actually live migrate the Zen virtual machine, but we live migrate QEMU, or we do anything that is happening to QEMU during a live migration. We also considered maybe we have to do something like a completely custom serialization and reinstallation protocol. But we settled to actually using execve here, which is a Linux system call that has all the features that we need. Execve is a system call that gets the path to a binary that you want to execute in a given address space, and it will execute exactly that inside the current address space. And it will retain the address space and the PID, which is good, because if you have other services relying on the QEMU PID remaining constant, then that's it. It will retain open files, sockets, and pipes, which is nice because that's exactly what QEMU is using across or to communicate with external components. And it will drop a couple of other things such as signals, timers, or shared memory. There's a question in the chat, and just checking, isn't the migration causing to use a new instance of VMware? So yeah, so that's actually what I was saying. So yes, we considered a local migration, and that would cause the start of a new QEMU. However, as Julian is already pointing out, migration is not always possible. And using execve is actually a much simpler and more straightforward solution. So there's really not a lot to it. You just add an execve call. You give it the path to the binary. You give it an array of environment variables, and you give it an array of parameters, and then you can re-execute whatever you want in your current address space. So now we have a third problem that is still open, and we need to somehow get all the state from the old QEMU to the new one. The nice feature here is that 50% of the problem is already solved, because QEMU is already supporting Zen live migration out of the box. And for that, QEMU already has a mechanism called SafeVM and LoadVM that allows you to take all the device model state, pack it up into a checkpoint file, and restart QEMU later on with this checkpoint file and load the device model state from there. So for device models themselves, we didn't have to do anything. We could just reuse that feature. On top of that, however, we need some more information here that is not going into the device model checkpoint, and that we had to add. And that is because QEMU is actually actively communicating with external components, such as the Zen console for serial PGY, for serial I/O, a VNC console, and other things. And let's take the serial console as an example. So when QEMU starts, it creates a PGY that Zen console is then later using to read and write the serial console of the virtual machine. And in EC2, you have a feature where you can actually read the serial output of your VM, and that is exactly using this mechanism. So we have Zen console attached to QEMU. And if you just plain restart QEMU, what is going to happen is QEMU will just create a new PTY, and Zen console listening on the old PTY will just not get any output anymore. So that's not what we want. So instead, we have to make sure that we're not creating a new PTY, but reusing the S61. And the nice feature here is that execve also already makes sure that the PTY, being a file descriptor, is retained across the restart. The only thing that we need to store in order to reuse it later is essentially the file descriptor of the PTY. The same goes for other resources here. One more interesting thing was that there are parts of QEMU state that do not go into the device model checkpoint. That is mostly PCI pass-through configuration. So QEMU is involved in SRIOV instances where we normally pass through the device access by emulating the PCI config space and the PCI bus for those devices. And that includes QEMU makes sure to map the virtual interrupts used to the actual physical interrupts. QEMU is emulating stuff like MSI handling and a couple of other PCI registers such as power management and emulated capability registers. As we're using those features, we had to come up with a way to put those into the checkpoint state as well. And we did that. We actually implemented kind of our own serialization mechanism for that. And with all that, we now create two checkpoints before a restart. One is the device model checkpoint using SafeVM. And the second one is another checkpoint that we put right next to the device model checkpoint that contains the additional state that we need. And with all that, we now have a mechanism that allows us to figure out what QEMU version is running. We can restart QEMU into a new version, reusing the existing address space and PID and keeping all the external connections open. And we have a checkpoint mechanism that allows us to save and store all this data. So now we got to operate that. And the first thing we have to do during operation is we have to restore the state upon a restart. So saving state is nice, but restore is actually what you want. For that, we add a new command line option to QEMU called --life upgrade, which gets a state file as a parameter. And when starting with --life upgrade, what we do in QEMU is we read the checkpoint for SafeVM, similar to what QEMU --load VM does. And on top of that, we do some additional initialization. And I'm giving you a code example here from the VNC implementation. So the VNC server that QEMU provides for others to obtain the VGA frame buffer state is actually made available externally by opening a socket, and others can connect to the socket and read it. Now, in the normal startup case, that's exactly what you want to do. However, as I just explained to you, in the upgrade case, we want to reuse the socket that is already there and that is part of our checkpoint state. So we went through QEMU, had a look at all the components that are relevant for our EC2 use case, and essentially sprinkled the initialization code with some checks, making sure that if we're doing a live upgrade right now rather than a full restart, we restore the file descriptor for the VNC socket from our state checkpoint file rather than creating a new one. And that was also pretty straightforward. So now, from the operational side, we're done. We tested that, we used it a couple of times, and turns out live upgrade in QEMU works pretty fine. It's mostly transparent to customers and has negligible downtime. And I say mostly transparent, I mean that essentially if a VM is just running and not doing any device I/O at the time of a QEMU live upgrade, the customer will not notice any difference. They will not see anything. If you are, however, interacting with QEMU at the time by doing serial I/O, by having a look at the PCI bus or something, then you might see a short delay in your operation because QEMU takes some time to restart. But this time is way below 100 milliseconds, and we haven't seen any issues with that in practical use. So that's fine. Now, it's all nice and such. We have now rolled out a new QEMU supporting live upgrade throughout the whole fleet. But remember, sometime before I told you we have very long running instances. And for those very long running instances, it's actually not possible to live upgrade, even though we now have a new version. So from a security handling perspective, we would like to get to a state where we can actually say, okay, all the fleet supports QEMU live upgrade, and whenever we have an issue with QEMU, we just roll out a new version of QEMU and trigger a live upgrade of all our instances. Unfortunately, that will not be possible until we get QEMU everywhere to a live upgradable state. One way to do so would be to ask all the customers running those long-running instances to just do a reboot or restart of the instance, and then they would just come up with a new QEMU. Unfortunately, that is a substantial pain for our customers, and we try to avoid those if you find other solutions. And in this case, we actually found a different solution. So question here is, can we make live upgrade for QEMU available without rebooting the guest or restarting QEMU? And the answer is yes. It turns out we can take our live upgrade code, especially the checkpointing part and the triggering of the restart, and wrap that in a shared library, and then inject the shared library into a running QEMU process. We didn't even have to implement that on our own. There are a couple of projects out there that do that. So the copy and restart project in user space has a tool called Compel that is able to exactly take a shared library and inject it in the running process. And there's another project on GitHub called Linux Inject, which has like 80+ forks where people do similar things. So this technology is out there, you can use it. And what it does is it takes your code, whatever you want, as a shared library, injects it into the running process, and executes the code or executes a constructor function as part of your shared library. And then in this constructor function, what we can do is we can gather our checkpoint state and we can trigger the restart. So I already said that the code that we wrap in this shared library is mostly a copy of the exec VE code that we have in live upgrade as well. So it's simply copy it to a shared library and build a shared library out of that. There's a couple of things that we don't need. So we don't need a specific QEMU command here, but we can just trigger the live upgrade as part of the load process of our shared library. And we also don't need the restore code because we're actually going to live upgrade into the already installed live upgrade capable version of QEMU. So the only thing that we have to do is we have to generate a additional live upgrade checkpoint that is binary compatible to what the regular live upgrade would do. And that is the last problem that we have to solve, because now what we're doing is we're building a shared library. And now we need to find all the interesting data that we want to put into this checkpoint somewhere in memory. Unfortunately, we're operating on a production system, and usually production systems don't have symbol information. So you can't just somehow query the production binary, hey, give me the address of the vCPU array in QEMU or of the VNC socket that we need to store somehow. And even if we were not in a production system, or if we had this symbol information available, it wouldn't be as straightforward, because you could still simply not query that from your shared library, because you'd have to think of building QEMU with -r dynamic to export symbols dynamically. And if you do not do that, then you just don't have this information available. Luckily, I already told you before that we have a database of all the QEMU builds that we ever shipped to our EC2 fleet. And this comes to the rescue here again, because we can go back to this database and actually have a look at the symbol information for all those builds. Build a small binary scanner, which you can imagine to be something like dwarf dump, just with a limited feature set. And what this scanner does is it looks at all the old builds and creates for every version that we ever shipped a map of memory locations that are interesting for us. And one of the examples is given at the bottom right here. What's in this memory map essentially is something like, okay, the VNC socket file descriptor is somewhere at a given address. It has a size of 4 because it's an integer, and it has an offset of 24 inside the data structure at this address. And with that information, what we can do now is our shared library can actually read the map for the currently running QEMU version. It can look up all the relevant data in the memory based on this information, and generate a checkpoint that is similar to the checkpoint that we had before. And that's pretty much it. So with that, what we have now is we have a live upgrade mechanism for QEMU. We can detect the running version, we can trigger re-execution, and we can transfer state from an old QEMU to a new one. And on top of that, we also found a mechanism to actually operate that and bring the whole fleet in EC2 into a state that it can live upgrade QEMU without having to restart any of our long-running EC2 instances. And that is the end of my talk. I thank you for your attention, and I'm happy to take any questions. Thank you, Stefano. Okay, so is the first question, and that is why didn't we put the PCI info into the VM data? Mostly because we were not sure whether that was a good idea at the time. It's something we might want to revisit, but for us, we said everything that we store on top of what SafeVM does should go into the separate state file. That was just a implementation decision at the time. There's another question for the binary scanner. Isn't there something like ASLR? Yes, that is true. I left the nitty-gritty details out here for the talk. Of course, so if you have a statically linked binary that is linked to the or running with a static link address, then our map is enough. If you have something like ASLR, where your code segment is relocated to other locations, you basically have to add the offset of the relocated text segment as well. And that works because we are still in control of them0. We can have a look at the proc maps file for this process, and we know where the text segment starts, and then we can simply add the offset there. Next question is from Ian. How much effort did this take? I'm for the original implementation for Light Upgrade, I think it took me about half a year designing and implementing that and getting it to the point where we could start testing it. And then we had it operational. The inject the Light Upgrade code as a shared library and roll it out took at least the same amount of time. Unfortunately, we can't be more specific here because it wasn't actually a subsequent 6 months of work, especially for the second project, but it was more working on it here and there, and actually rolling it out took much longer than those 6 months because there were other things coming up in between. Yep, it was certainly fun, and definitely a lot of technical details that you came across, and a lot of bug hunting where you spend days or weeks hunting for certain things and just to figure out that your checkpoint state is missing a certain bit or something. Stefano was asking if there's a dirty tracking of some sort. QEMU is paused at the time of the live upgrade, similar to what you do in live migration. So live migration also stops any processing of new events from QEMU before it does any work, and makes sure that pending IO operations, such as block IO operations going on, are flashed before the live upgrade state is taken. And we do a similar thing. So QEMU is not processing any events while doing the live upgrade. And as the period we take for the live upgrade is fairly short, we haven't encountered any issues because of that. So one question is whether we use it for patching security issues or for regular updates. That goes deep into the operational part. So we're not using it in every rollout, mostly because it's triggering an additional risk, and taking that risk only makes sense if you really need to fix the risk. And that's why using it in security situations is the one thing where you want to do that. Just for a regular new rollout of QEMU, you're happy to run your old version of QEMU as long as it is safe. Okay, we'll take probably half a minute or so before the next talk. All right. Thank you all very much.